Well, hello everybody, and thanks for everyone who's attending live, plus all of those who will be watching the recording later. My name is Aaron Standard, and I'm one of the creators of the Akadot project. And I'm joined by Gregorius, who works with me here at Petabridge. And I guess we're going to go ahead and get started real quickly by covering some of the Akka.NET release stuff we've been doing, and then that way we can get to our show and tell presentation, which is going to be all about .NET systems programming and about some of the work we've done pretty recently, including in the Akka.NET 1.44 release, trying to improve performance and what some of the techniques are that you can apply to your own applications, even if you aren't, working on a major open source framework like us. All this information is still totally relevant. Um, so why don't we go ahead and dive into talking a bit about our release schedule. So I guess the first thing that we've done recently that we should discuss is
Mhm.
the newest release of Akka hosting. So Gregorius, do you want to take this one?
Yes, sir. For Akadot hosting, we just released 0.5.0 15 days ago. This release contains two major user quality of life improvement. Basically, one is that the Akka persistent SQL Server hosting now supports options, so you can actually configure it however you want. You're not limited to the API anymore. And the second thing is Akka Hosting Test Kit, which is a module that you can use to actually create unit tests using the hosting package.
And so we basically decided that this was a worthwhile experiment, this Akka hosting test kit, primarily because when we were doing some work with some, Petabridge customers, we found ourselves writing our own essentially like poor man's version of this stuff anyway, because it's so useful for doing integration tests, basically, is what we
Mhm.
we found it to be really useful for. So this offers kind of a built-in way of using the test kit methods with an actor system that's built using an I hosted service essentially behind the scenes, and uses the dependency injection containers, can use your Akka configuration and so forth. Now, this isn't a good choice for, let's say, trying to do unit tests on things like individual actor types. The test kit's still probably the cheapest way of doing that. But if you need to integrate your actors with, let's say, a custom entity framework context, or you need to integrate it with a web API you've been building, or maybe a gRPC or a SignalR endpoint, this is a really good set of options for being able to do that. It'll allow you to unit test your actors in the context of all the other services that might be running behind your system. So we haven't actually started using this package ourselves in any of our projects just yet. Um, and that's mostly my fault since I've been out of the country for most of the past month. Um, but we are looking forward to giving this a try. And then the other
Mhm.
big release that you were managing, Gregorius, is our newest Akka hosting release. And you've spent a lot of time and trouble, not Akka hosting, Akka management. And you've spent a lot of
Mhm.
time and trouble documenting how all this works. So why don't you take us into the Akka management zero point 0.3 release that we just did?
Yeah, the biggest thing that happens in zero point 0.3 is Akka Coordination Azure support, which allows you to actually use lease, cloud-based lease in basically like split brain resolver or cluster sharding and stuff like that. And we added a bunch of programmatic helper classes for basically all of the discovery modules, AWS and Azure and Kubernetes and all that stuff. And we do one uh, API breaking change in discovery at Azure is in that instead of passing in default Azure credential, you can now pass in token credential. It's not um, code breaking, but it is binary breaking. So yeah.
Well, so it's basically so it's source compatible, but not binary compatible, which I don't think is a huge deal breaker in this case because I don't think anybody had built any libraries on top of that. Um,
Hmm.
but long story short, the biggest thing we added here is this Akka coordination.azure. This is basically a distributed lock, is what it is. And it's a
Hmm.
better split brain resolution tool than a lot of the algorithms that are built directly into Akka.cluster itself for particularly large clusters. The problem that these distributed locks really help with is what we call partially connected nodes. This is when you have, let's say, a pretty big cluster, let's say over 100 processes that are all running Akka.net, and you start to experience, let's say, busyness, or maybe you have like a software network address translation layer that's responsible for doing routing between different virtual machines on your network. If you start seeing some congestion in some of those areas, what you'll start to notice is rather than there being a clean split in the cluster where these nodes don't see these nodes and those nodes don't see, basically no one sees anybody else, you end up with these like blind spots where node A can see B, but it can't see node C, but node C still thinks it can see B, and node B can still see both. And so it's not clean in that case. So using a distributed lock allows us to say, okay, whoever the leader is who grabs that lock first, its point of view is now the source of truth, and it can kill everybody else in the cluster that it can't see. And that gives us a fairly clean way of being able to resolve a split brain when that type of scenario happens. That's usually a function of congestion on the network or a really high CPU utilization, is what would cause that. So we're looking to get Akka hosting and Akka management. This is kind of part of our future releases. We're making pretty good progress towards getting both of these released to market and finalizing the APIs. We've got some changes we're considering making to Akka hosting. I think I'm going to change the default way Hokon gets added on there because users keep foot gunning themselves, assuming that it's going to overwrite default Hokon when by default it doesn't. It just kind of appends it. So we're going to flip that default around, I think, in order to make it do what people expect. Um, and then we've also got a couple little things left to do around Akka management and Akka hosting to kind of just finalize the API surface area and put it all to bed. Now, the big release we just did recently is Akka.NET 1.44 and Akka.NET 1.5 Alpha 2. Looks like I forgot to link to the release notes in both of those cases, but luckily they are right here. We just released both of these on Monday. Akka.NET 1.4.44 basically has a bunch of performance fixes inside of it, particularly for users who are running Akka remote. So this is actually where I like data mined all the content for my presentation I'm about to give. All came from the performance improvements that went into Akka.NET 1.444. Um, so we eliminated delegate allocations in the fork join dispatcher. We also eliminated some allocations that were happening inside the mailbox, meaning literally every time an actor got scheduled to process messages, we got hit with this. Some boxing allocations. We got rid of allocations from the default log message formatter. You should see total memory consumption go down in this release of Akka.NET, and you should see throughput improve for both in-memory messaging as well as going over Akka remote as well. And we'll go into some detail on these performance fixes during our show and tell. Now, the next thing we should talk a little bit about is the Akka.NET 1.5 roadmap. So we had originally been telling users that we were targeting the month of September to deliver this. Obviously, it's mid-October now, and we have not delivered it. And I feel like we should explain why. Here inside Petabridge, we are actually in the process of prioritizing a project that is basically not yet ready for demonstration purposes yet because I've got a couple other things I got to wrap up this week before I get back to work on it. But we're in the process of building a cloud-based monitoring and management system for Akka cluster. It's going to be called Akka.NET Ops Center. It's going to be the name of it. And this is going to include both a free and a paid tier. The free tier will give everybody the ability to connect their cluster to it, the ability to see what's happening inside of it, how many nodes are available. We're also going to expose some basic actor metrics, show you the history of the cluster and how things are working. the paid tier, we haven't totally decided what's going to be in there yet, will include some things like alerting rules and the ability to invoke Petabridge.command remotely using your Azure Active Directory tenant or something like that. So we're kind of prioritizing that ahead of Akadon 1.5 right now. Now, don't get me wrong, we're still working on Akadon 1.5 milestones. Gregorius himself has been very busy on implementing our testing compatibility matrix for the new CQRS features we're trying to build into Akka persistence right now, which is a pretty large project in and of itself. And the one thing I'm not able to work on that we need as part of 1.5 is the new artery transport for Akka remote. All my bandwidth that would be going on that is going towards our Ops Center project right now. So, in terms of when we expect to get this released, we're probably looking at Q1 of 2023 rather than Q3 of 2022. That's probably when this is going to finally ship and be in the hands of end users. Obviously, we'd like to get it done sooner, but we have to go ahead and prioritize what's going to allow us to continue to scale our company and hire more developers and do all that sort of stuff. So that's kind of where things stand with respect to the Akka.net roadmap right now. Gregorius, do you have anything to add before we move on to our show and tell presentation?
Just a minor thing for the Akka hosting test kit. There's a slight change in that the way things are being done. You might notice something wrong, something weird, like if you convert your old unit test to use Akka hosting test kit, that your test time drops significantly, like from 300 millisecond to like 80 or 60 millisecond. That's normal because all of the setup times, like all of the actor system setup and all that, are moved outside of the test inside of instead of being done while the test is being set up.
It all happens as part of an external fixture, is what you're saying.
It's more like a fixture.
Yeah,
It's called asynchronously just before the test is being started.
gotcha. Okay, so the latency is still there; it's just not being measured the same way. Um,
Hmm.
got it. Okay. All right. Well, without any further ado, then I'm going to go ahead and lead us into our presentation for today. So let me go ahead and go full screen here just so everybody can see the code samples. And I'll hide our little banner. So I just gave this presentation in person in the Netherlands last week, and I'm going to go ahead and give it again because that it wasn't recorded at Techorama. Techorama is a fantastic conference, but they have something like 12 to 14 tracks running in parallel every hour or so. So a lot of overhead to be able to record all of that. But no problem. I'm happy to go ahead and give it again here and make it available on YouTube. So let's get started. So yeah, this talk is all about .NET systems programming learned the hard way. So a little bit about me. I mean, many of you from the Akadonic community probably know that I, of course, am involved in the Akadonic project. But my background with .NET starts in 2005. I got a college internship at a company here in the United States called the Fair Isaac Corporation. They're the ones who developed your FICO score that they use to compute your credit worthiness when you're applying for a mortgage. So I learned .NET there originally. I built large scale software as a service on top of .NET after I left Microsoft in 2012. We did real time marketing automation and analytics. And our second product, our marketing automation product, required the ability to process campaigns in parallel for tens of millions of active users concurrently. And we had to be able to do this with like, sub-second latencies, being able to process those results. And that really required us to build a stateful reactive programming model on top of our .NET services to do that. Turns out the actor model was a fantastic fit for doing that. And that's kind of where Akka.net originated from. And this is what I work on pretty much full time since 2015 is the Akka.net project and serving its users and our paid customers. But the key takeaway from this talk is that performance is a critical feature of Aki.net. That was kind of the biggest feature of the 1.44 release. And we're going to talk about some of the things you need to know about the underlying .NET systems that make up the common language runtime and the garbage collector and the thread pool. We need to know a little bit about how all these systems work in order to make sure we get the lowest possible latency with the least amount of memory and the highest possible throughput. So, in terms of all the different parts of .NET that are worth learning, the garbage collector is probably the highest impact area that can affect your performance. Now, the way garbage collection works in .NET is via what's called object roots, essentially, where, and if you take a look at this diagram here, object number 7 is no longer rooted. This means that any objects that previously referenced object 7 have either been nulled out or they've also been collected. In which case, that means that object 7 is no longer referenced by anything. It's not a rooted object any longer, and it can be collected by the .NET garbage collector when it's scheduled to run. And so when the .NET garbage collector runs, it's going to deallocate those objects that are no longer rooted. But also importantly, what it's going to do is in addition to deallocating those unused objects, all of the objects that are actively being used will periodically get compacted in memory. What this means is that we're actually going to move that object from its previous location into a new location in memory. And the reason why this is done is to improve performance in a number of key ways. One is that it makes it a lot cheaper to allocate new objects in the future because you can do it at the top of the heap. This helps keep things like Gen 0 and Gen 1 garbage collection really inexpensive because we don't have to do compaction again for those short-lived objects. And then on top of that, it also makes it so we don't have to do a lot of complicated searching in the working set. That's the set of memory that's been allocated to your process by the operating system. We don't have to go ahead and do a bunch of complex searching to find a block that'll fit for us. All of the used blocks are all compacted together in memory, and all the free blocks, ideally, will sit after that. Now, that's not quite that simple in terms of how it works. The garbage collector has a number of different metrics it'll make compaction decisions on, but this is kind of the general principle and how it functions. Now, if I go back through my slides here, the next thing to learn about the way the garbage collector in .NET works is the different generations of garbage collection, and there are 4 of them. There's Gen 0, which is the cheapest form of garbage collection. This happens very quickly after objects have been allocated. And so, for instance, let's say if you create a string and print it out to the console and then don't use it anymore, that would very likely be a Gen 0 object. It's essentially doesn't get rooted for very long. So we can allocate it and then very quickly deallocate it. And then we don't need to do any compaction because we allocated it essentially at the very top of the heap. Gen 1 is a little bit more expensive. Gen 1 objects are ones that have survived one generation, one instance of Gen 0 garbage collection. So they were rooted for a longer period of time and possibly by more objects. So we weren't able to collect it. But when it gets unrooted later and we're free to collect it, that form of Gen 1 garbage collection is still fairly inexpensive. That memory is going to be slightly more fragmented. So there is going to be a higher compaction cost that we have to bear, but it's still going to be a lot cheaper compared to Gen 2 and large object heap collection rounds. Gen 2 garbage collection is the most expensive of sort of the normal GC flavors. These are for objects that have survived at least one round of Gen 1 garbage collection. And objects that live in Gen 2 tend to get highly fragmented, and they might have to essentially, we might have to incur a lot more what are called garbage collection pauses to move Gen 2 objects around. Now, the most expensive form of garbage collection, though, is the large object heap. These are objects that are at least 85,000 bytes in size. And they're treated differently because at this stage, the amount of memory these objects use is much larger than what can fit. Oh, let me rephrase that. Is typically larger than what can fit into a single page of memory. And so compacting that means moving across page boundaries in memory, which is a lot more complex than it is for smaller objects that use less than that. So these objects tend to get collected much less frequently. And these are the source of all sorts of interesting quirks and problems in .NET for a long time. A good example for those of you who've been working in .NET since the early days of .NET Framework. The reason why Internet Information Services, IIS, the web server built into Windows, the reason why IIS used things like app pool recycling was because the large object heap actually didn't get garbage collected at all and would result in huge amounts of memory fragmentation and would cause processes to eventually slow down. One of the other costs behind, let's say, memory usage in .NET and really any programming language or any runtime is that when your memory is, let's say, all the memory you're using is adjacent to each other inside the actual registers in your DRAM or inside your L1 or your L2 cache on your CPU, that sequential access time is very beneficial for things like cache affinity, processor affinity, being able to make sure that all of the data from the memory bus gets transmitted to the CPU with the fewest number of instructions. Um, those are all, so sequential memory access is a good thing. When we have random memory access, where we're accessing objects from all sorts of different locations in memory, the bus speed of our memory chips begins to become a factor, and that typically is much slower than our CPU clock times are. So there's going to be some cost to that. So one of the other reasons why we do compaction, in addition to being able to make it cheaper to find free segments of memory, is to try to help frequently accessed objects appear sequentially in memory to each other. That's one of the other goals behind doing this. Same sort of principle as defragmenting your hard drive, but memory is a little bit more more robust than disks are from that point of view. So this is it. And basically the general sort of performance principle around the generations of garbage collection is that Gen 0 and Gen 1 are cheap, Gen 2 and the large object heap are not. They tend to be more expensive. And they also contribute to memory fragmentation in ways that Gen 0 and Gen 1 do not. So the .NET memory model, let's go ahead and imagine that we have this field and this method on an instance of an object inside our application. Well, the stack, which is one part of the .NET memory model, the stack is everything that's being executed in a thread at any given time right now. So meaning that these are actual application instructions that are being executed on a CPU. And so we have a stack, and then we have the managed heap. The heap is all of the managed in-memory objects that belong to the .NET processes shared memory. That's going to include, for instance, this stack is going to have a reference to this method instance on this object. So that's going to be one pointer into the heap. And then on top of that, this random object. So this is a static object built into the CLR. That's also going to live on the managed heap. And then we have down here, we're using this random object to generate a couple of integers. These integers are value types, also known as structs. Structs are stack only data structures, meaning that they only get allocated into, let's say, stack memory while they're being used. And then once this scope exits, the stack's going to essentially clean up all these memory references and move on to the next instruction, or it's maybe going to move back to an outer scope. And all these variables are going to be unscoped, and that memory will be instantly freed without any garbage collection. So that's kind of the idea behind stack only types, is that they are designed to be very ephemeral, only used in a highly localized context, and they don't require garbage collection. They aren't part of the managed heap. Now, when you declare a property on, let's say, a class you've defined that implements a value type like an integer, we're going to allocate that integer's value onto the managed heap because that's part of a larger a larger managed data structure when we do that. But when we're just declaring inline variables like this, we don't. But they get allocated just directly into the stack for everything that's running through the current thread right now. Now notice down here, when I add my two integers together and I call to string, that string is going to be allocated onto the heap. You can see that in this little arrow right here. That's going to be a Gen 0 object, more than likely, where as soon as this method exits, there's nothing rooting that string anymore. Therefore, the garbage collector can instantly free it up, and we don't have to worry about it any longer. Whereas this random.shared object right here, this is a static object that's going to live for as long as our process does. That's going to live in Gen 2 garbage collection, and it's going to stay there forever, meaning that the garbage collector is not going to attempt to collect that object because it's always rooted because it's a static reference. Whereas this class that call this do thing method, this could be a Gen 0 or a Gen 1 object, dependent upon how it was allocated, how it was referenced, and how it's being used. So this is sort of the gist of what the memory model in .NET looks like. Where this starts to impact performance is basically where the generations of allocations occur. Gen 0 and Gen 1 are fairly inexpensive forms of garbage collection. The reason why is compaction costs are very short. All these objects tend to be allocated together in memory at the top of the heap. But you can also try to eliminate Gen 0 and Gen 1 allocations as well by using, for instance, structs instead of classes. You can also go ahead and do things like try to make sure you only declare your reference types in a very narrow scope so you can guarantee they make it into the lower generations of garbage collection. Now, on the flip side, if you aren't able to, let's say, avoid Gen 2 garbage collection, the other strategy you can try to use to minimize it, to minimize the impact of the actual garbage collection operation, pausing your application in order to free up memory and to compact it. One of the other strategies you can use is keep Gen 2 objects in Gen 2 forever. So there's not going to be any garbage collection overhead for objects that are still rooted because we're going to be able to instantly see this object still has roots from other parts of our application. Therefore, we can't free those up and collect them right now. So one example of being able to keep objects in Gen 2 forever is using object pools. So, for instance, in Akka.net, I think several releases ago, we started using the Microsoft.extensions object pool type for being able to pool string builders inside our JSON serialization system. The best candidates for object pools are reusable types. String builders are a really good example of this. In areas like Roslyn, for instance, the .NET compiler, they use pooled string builders quite heavily. Other examples of this might be things like reusable stream types. But the other really common candidate for object pools are actually byte arrays. If you're doing a lot of work with file I/O, or maybe you're doing a lot of serialization, you can use some of these system.memory types for this purpose exactly, such as the memory pool object for doing that. Now, the idea behind this is that rather than constantly using the new keyword to create new byte arrays or new string builders, we essentially have a fixed size pool that is usually initialized statically, meaning that once the process starts, we go ahead and we allocate a fixed size, let's say, pool of 1024 string builders, or maybe we create a memory pool of 16 megabytes worth of buffer space. And we make that available for use inside our serialization layer or maybe our disk IO layer. So we go ahead and we will rent an object from the pool, use it to do some work. And once we're done with it, we will return it to the pool and maybe zero out its memory or dump its contents if it has some temporary state that we've used. And these don't cause additional memory allocations when we do this. We're essentially able to reuse the same types over same instances over and over again without having to allocate new ones. This will result in a decrease in garbage collection pressure, and the amount of memory usage we have will remain somewhat constant around these areas. So, an example of where we used object pool successfully was our Newtonsoft serializer in Akka.net. This is the default Akka.remote and Akka.persistent serializer. So we have a object pool of string builders that is declared statically inside Akka.net. We call string pool builder.get when we're ready to use one. We pass it into our string writer that we're going to use with JSON.net, and we're going to call serializer.serialize using that string builder. And then finally, once this piece of code is done executing, we're going to return this object back to the pool. What does the performance impact of this look like? Well, we have these benchmarks that we ran, including scenarios where pooling was not enabled and scenarios where it was. And you can see here that when we turned pooling on, we eliminated about 30% of total memory usage from our application. And we also were able to reduce Gen 1 garbage allocation entirely. So we moved everything from Gen 1 down to Gen 0. And on top of that, Gen 0 allocations themselves are also down as well. On top of that, in scenarios where we're using these pooled string builders across a large number of threads, which is, I'm going to get into why we need to do this, but something else you should look at benchmarking. When we do this across multiple threads, we also saw a 28% throughput improvement in concurrent cases. So even in scenarios where we had lots of different threads all renting and returning their own string builders, we still were able to improve end-to-end serialization performance quite a bit inside the system. So that's one of the ways we can go ahead and keep objects in Gen 2 forever. Now, the next thing worth learning about in terms of the garbage collector, we've talked a bit about the way it works. We've talked a bit about the generations. What about the different configuration options we can use to performance tune garbage collection? Now, when I gave this talk in the Netherlands last Thursday, one of the attendees came up and told me at the end of the day that he had texted this slide that I'm about to show you to his coworkers, and they were able to get a 300% performance improvement by implementing this configuration change I'm about to show you in one afternoon. So if you're going to pay attention to anything in this talk, this is probably these two slides are the ones you should pay attention to. There's several different modes for garbage collection in .NET. By default, all applications use what we call workstation garbage collection. This is designed for client-side applications, so command line apps, MAUI apps, Windows Forms, etc. These applications have a very simple form of garbage collection that basically runs on user threads, meaning that when you trigger garbage collection inside your application, the thread that triggers it is going to be the one that performs it. So it's going to be blocking garbage collection that's going to suspend your thread in order to compact memory and also deallocate objects that are no longer used. Behind the scenes, we also have what's called background garbage collection, which has been enabled by default for some time. And what this is going to do is it's going to take all of the really expensive Gen 2 garbage collection, and this is true for Workstation GC as well. Basically, Gen 2 garbage collection is no longer going to happen on your user threads because it's so expensive. Ditto with large object heap. That's all going to happen on a set of background threads that are managed by the CLR itself. So that's background garbage collection, and that's enabled by default. That's going to move the most expensive form of garbage collection off of your threads. Gen 0 and Gen 1 are still going to be done in the foreground, though, on Workstation GC. Now, the interesting part is server side garbage collection. This is ideal for server side apps like ASP.NET and also really good for Akka.NET as well, I might mention. The idea behind this is that garbage collection, generally speaking, is going to occur on dedicated threads running at a high priority on the system. So GC is going to have a chance to run before your user code does. You can still, reduce the frequency with which GC runs by following some of these practices we're going to cover in this presentation. But GC basically now runs totally asynchronously to your code. However, the really big change that server mode garbage collection enables is that rather than having one dedicated GC thread for your entire process, we now have a dedicated GC thread and a dedicated heap for each logical CPU that is running inside your application. This means that when one core is performing garbage collection, none of the other cores are blocked. So what this is going to do when we turn on server GC is essentially make it so garbage collection is no longer an operation that is global. Rather, it's scoped down locally to an individual CPU in your machine. This will greatly help improve throughput and will reduce, let's say, sort of side effects from garbage collection. The downside of server mode GC is that it's going to use more memory and it's also going to use more CPU. So it's more expensive from a resource consumption standpoint, but it's going to allow your application to run with much lower latency when you do that. So the one trade-off that you should bear in mind is that if you have a super densely packed environment, let's say you're running hundreds of apps all on the same machine, you probably don't want all of them running in server mode GC as they'll all start to have these sort of cumulative side effects on each other. Whereas if you have servers where you have a relatively lower amount of tenancy on it, let's say only one or two apps or maybe 1 to 10 apps running on there, server mode GC is the way to go. So server mode GC is not enabled by default. You have to enable it either via there's a runtime settings.json file that can enable it. I believe there's a environment variable that can enable it. The way I prefer to do it is actually in our CS project file. I'll go ahead and enable it inside this little project in my C# project here. Server garbage collection is true. Now, let's go ahead and take a look at the remote ping pong benchmark, which is what we use for measuring latency and throughput in Akka.remote. With workstation garbage collection, and I believe this is running on .NET Core 3.1. With workstation garbage collection on .NET Core 3.1, we're averaging across most of our benchmarks in the ballpark of 145,000 messages per second. And that's true when we scale the load up and we increase the parallelism and increase the threads. That number stays pretty constant. On .NET Core 3.1, when we enable server mode garbage collection, we're now doing about 300,000 messages per second rather than 145,000. So you're looking at a 2x improvement in total throughput inside the system. One other thing you'll notice is that the thread counts are significantly higher in our server mode GC versus our workstation GC. And that's by design. The reason being is that we have those additional dedicated threads for performing garbage collection when we're running in server mode. And so the thread counts are definitely noticeably higher when you're running in server mode GC. But for us, since we're interested in building low latency applications, this is the right trade-off for us. So server mode GC is one of the cheapest things you can do to have a really high impact on your performance. Now, that's all the details I sort of have around the actual way the garbage collector works. The next big chunk of this presentation is all about how to make the garbage collector not need to work so hard. So how can we reduce memory allocations or eliminate them altogether? What are some techniques we can use to try to do this? Well, one really nasty source of allocations in really busy parts of Akka.net, as it turns out, is delegate allocations. So this is the mailbox run method. This method runs billions of times per second in benchmarks like remote ping pong, for instance. And basically, this is part of the critical path of actor message processing. So this is a super high performance area of Akka.net. This little line right here, actor.useThread context, looks like it's not closing over anything, but it really is. It's closing over the this keyword implicitly with the way it's designed. That's because this process all system messages and process mailbox methods are instance methods on this class. So every time you allocate a lambda function like this, we're actually creating an anonymous object that lives on the heap in C sharp. And that's going to result in a minimum of 32 bytes of allocations. If you perform closures when you write that lambda, that number is going to go up. We're going to allocate more than 32 bytes when we do that. So one thing we can do to try to eliminate a source of allocations here is, well, actually, first we should benchmark it, which we did. And so in this case, the number that we want to take a look at, I'm going to grab my pen, is the run performance. This is the amount of memory that we're allocating, having a single actor process 10,000 messages versus 100,000. So it looks like we're generating, every time we have an actor process 10,000 messages, we're generating 21 kilobits of memory allocations. And of course, when we 10x that, we see a nearly 10x increase in memory allocations as well. So one way we can eliminate these delegate allocations is by simply inlining the delegate. So in this case, the delegate was just performing some static work on the actor cell. This is basically how we register who's the currently executing actor on this thread, is what we were doing. So rather than use a delegate function for that, I went ahead and I just moved that code from inside the actor cell to inside the mailbox. So I added this try block and this finally block down here, and we no longer need a delegate to run this. We were able to eliminate, by the looks of it, about 100% of memory allocations when we did this. We went from allocating 21 and 203 kilobits to exactly 1008 bytes. So wherever this is being allocated from is probably a fixed size sort of operation somewhere. Not really important for us to try to eliminate that. But the fact that we're able to eliminate all these delegate allocations will result in a lot less garbage collection needing to happen every time an actor processes messages. So if you multiply this times the billions of times this operation gets run in any given second on a busy system, that's actually quite a big amount of memory savings and reduced garbage collection pressure happening right there. We also, improved the throughput of processing an actor's mailbox by about 10% when we did this. Now, there's other techniques for eliminating delegate allocations aside from inlining it. Some people may not like inlining a delegate because maybe the delegate actually performs some fairly complex work. Well, one technique you can do is using in C#9, you can declare a static delegate. This means that the compiler is only going to allocate a single instance of that method. Therefore, any state you want to pass into it, you have to pass in explicitly as references. So you go ahead and need to declare parameters and then pass your parameters in, and then the delegate can operate off of them that way. That's a perfectly fine way of eliminating allocations as well, going down that route. The other technique we can use to eliminate delegates is to just simply cache our delegates or use the expression compiler. We do this in several areas on the internals of Akka.net and places where we can't inline, and we can't use static delegates yet because we're targeting .NET Standard 2.0 inside Akka.net 1.4. The other technique we can use that's very fun is what's called a value delegate, which I'm going to show you next. So this iRunnable interface right here is part of the dedicated thread pool, which runs the fork join dispatcher in Akka.net. So this gets used to run Akka remote, Akka persistence, cluster sharding, all that stuff. And we were in the process of getting rid of delegate allocations inside of this system as well as part of the Akka.net 1.44 release. Well, one thing you can do if you want to avoid heap allocations altogether is we can take an interface that has a generic method like run on just a little void method. And rather than pass in a delegate, we can simply create a value type like a struct that'll go ahead and implement this interface method down here. And so this will still run the exact same way it would have before, but we're not allocating anything on the heap when we do this. We're only allocating stuff inside the stack when this is being executed. Now, we do have to worry about possibly, let's say, this queue user work item method down here. This might end up resulting in what's called a boxing allocation, which we're going to talk about later. This is what happens when a value type is casted into, let's say, an object or a reference type. And that's going to actually result in the value type being pickled onto the managed heap. So even though we thought we were saving on allocations using these value types, we ended up accidentally creating a heap allocation anyway. Other sources of allocations that you want to be mindful of are things like empty collections, and I'm using empty in sort of finger quotes here. So I use JetBrains Writer quite a bit these days. It's my primary IDE. And JetBrains Writer has a really valuable feature on it called dynamic program analysis. In fact, I'll pull that up real quick in my browser here. So this little icon down on the bottom right, whenever I'm running my application in debug mode, Writer will go ahead and look for closures, large object heap, and small object heap allocations. And I can set little thresholds here for trying to inspect how big do those allocations need to be before Writer makes a mention of it. Well, Writer is able to go ahead and determine when I run, let's say, the remote ping pong benchmark in debug mode, that most of my allocations come from, looks like protobuf deserialization here. Or maybe I'm allocating bytes when I'm calling, let's say, my 2 byte buffer method for allocating. Let's see, where is that actually? Allocating memory for use inside Akka.remote. Okay, this is all really useful information for us. Well, one thing I noticed when I was taking a look at the data from dynamic program analysis is that we were allocating a large number of list objects. And I thought, okay, that shouldn't be something we do a lot of. What could possibly be causing that? And lo and behold, it was this code from like 2014 that was causing it, which is that we are not allowed to have a null list of replies because that's just the way this API works inside the finite state machine actor. So we're allocating a brand new list each time. Well, guess what? Every time we allocate this list, it's going to create a 32 byte, excuse me, heap allocation. That's going to show up quite a bit when we're generating millions of these every single minute. So one of the things we can do really inexpensively to basically to obey our API construct, namely that we're not allowed to have a null set of replies, is to use a statically initialized empty collection using the array.empty type, or maybe I could use the immutable list.empty type here as well. Those would both work just fine. But this allowed me to go ahead and eliminate that source of allocations in entirety. Again, we're just trying to look for some low hanging fruit we can easily get rid of without needing to break public APIs or change our wire formats. And these sorts of wins really do help add up to make Akka.net a lot faster each time we do this. Now, value types are another interesting area where we can make some pretty significant performance improvements in Akka.net. For instance, this is a reference type that in Akka.net 1.443 existed inside the finite state machine class, which we use for managing things like Akka.remote, for instance. And I noticed, okay, we allocate millions of these per second, and these are all really simple reference types that get used in a very tight scope inside our FSM actor. And if I benchmark how much memory does an FSM actor use when processing messages versus an untyped actor, we can see that an FSM actor uses about 6 times as much memory as a normal untyped actor does. Slightly less than 6 times, but still, that's kind of the rough ballpark. Now, if I change this class to a read-only struct, I instantly get a memory savings of 30 megabytes here. And that's because these value types, these structs, actually use smaller memory as a percentage, as a smaller amount of memory as a percentage of the whole. They're using, I think in this case, instead of 32 bytes, they might be 28 bytes each. So they tend to be aligned a lot shorter than an equivalent reference type would on the heap. So that's a huge benefit there. And let's see if there are any savings on garbage collection. Yes, there were. We also cut Gen 2 garbage collection in half from 2,000 to 1,000 for the FSM actor. So we were able to eliminate Gen 2 GC altogether by changing this to a value type. So again, a very inexpensive cost savings. And there was definitely a minor throughput improvement for getting rid of some of the Gen 2 GC. However, there are some other basically, let's say, trade-offs that come with using value types. One is that you can accidentally run into what we call boxing allocations. I just explained a minute ago, boxing occurs implicitly when a struct gets cast into an object. And that can happen in really subtle ways. So basically, what happens is that struct gets wrapped into an object and placed on the managed heap. So even though you thought you were getting all these cost savings from having value types, they're really still being treated as reference types somewhere in your code. So the thing that got us in trouble here is we have these two different state name types here. These are typically implemented as enumerables or enums in Akka.net. And they're basically doing an equals check here. Is my current state the same as my next state? And as long as these two are the same, then we're going to basically not do any of our transition work. That's kind of what we're testing for here. But get a load of the method signature. This equals method is going to cast my value type into a reference type back into an object. And that's going to create boxing inside my application. In fact, Ryder was able to point out that when I was running my benchmark, we generated about 500 megs worth of memory pressure here just from running this dot equals method, which should never allocate in any circumstance. So what we're going to do is we're going to actually take advantage of a .NET language feature that's really nice compared to, let's say, the JVM or other programming languages, which is generics. So one way we can avoid a boxing allocation here is just making sure that we don't cast our value type back into a reference type. Don't cast it back into an object. So what we're going to do is we're going to use this call site right here, this equality comparer T state, where T state's a generic that's defined on our finite state machine actor dot default, and we're going to perform a comparison against both of these two. The method signature here takes two objects of type T state internally, and then we'll implement a method that uses integers under the covers to compare these two values. So this is functionally equivalent to what we were doing before, but it avoids that boxing allocation. So there are no more allocations happening at all at this call site. That's one thing you have to be a little mindful of when you're working with value types is that there's a lot of methods in .NET that operate primarily off of objects, that object-based class. And when you cast a value type into an object, you're going to create opportunity for boxing potentially. So again, that's where a tool like Writer's dynamic profiling can really help a lot, help us identify some of these. Now, here's where things get really interesting. The semantics between how value types and reference types get passed around our application are quite different. This is something you probably learned very early on when you're working with .NET. This is the envelope data structure. This is what we use for passing a message. When you call iactref.tell, we allocate one of these and we stick it in a concurrent queue. That's basically what mailboxes are doing under the covers. Well, one thing that we noticed is that we generate quite a large number of allocations inside our mailbox structure when we're queuing up even a relatively small number of these envelopes here. Just 10,000 envelopes will generate 394 kilobits, and 100,000 will generate 3.1 megs of memory usage. Well, what happens if I change that value type into a reference type? Well, you'll notice that we go from, let's say, 3.1 megabytes to 2.1 megabytes, or 394 kilobytes to 264. So a memory savings of about 33%. And then on top of that, we also see a significant performance improvement in terms of our memory usage. So what's going on here? What's causing this performance improvement inside our data structures? Well, there's a couple of reasons why moving from a value type to a reference type may have actually decreased memory usage. The reason why is that value types follow copy by value semantics. When I pass, let's say, an integer from one function to another, I'm not passing a reference to that integer in memory. I'm literally going to copy the integer's value into a new register that's going to execute in that stack. So passing around these structures can create quite a bit of copying. Now you can use what's called a reference parameter to essentially have one function reference another function's stack allocated memory. And that can work really well in tight loops, but it's not going to work well across multi-threaded sort of asynchronous programming boundaries like the type that you run into when you're using iactref.tell, or if you use an await call. That's just not going to work. You're going to need to have a copy by value semantic in there. Now, excessive copying can actually be more expensive than just allocating a reference. That's one of the things that our benchmark showed, is that on a single thread, when we were processing all those in queue operations, just passing in that reference once actually ended up being cheaper than having to copy that struct over and over again, because I have my iactref.tell, which copies that envelope into the actor cell, which copies it into the mailbox, which copies it into a concurrent queue. So there's at least 4 copy operations happening every time I invoke that method. So excessive copying can actually be more expensive than allocating a reference. So we shouldn't try to make everything magically into structs. They're not a silver bullet. We should use reference types when the semantics are actually referential. And then on top of that, we just want to just be mindful of what the right tool for the job is. However, here's where things get tricky. This will set me up for my next topic I want to get into. In addition to having to worry about, let's say, the memory pressure of copying structs over and over again on a single thread, what happens when we run this benchmark across multiple threads, which is exactly the way you'd expect a concurrent programming framework like Akka.NET to run? I didn't come up with this myself. Another contributor in the Akka.NET team told me, hey, Aaron, before you consider this change, you should really try running a multi-threaded benchmark on that code. And so I said, sure, let's check that out. So what happens when we significantly increase the amount of cross-thread message traffic? Where in this case, we came up with a benchmark where I'm going to create, I didn't format this table very well. Sorry about that. I'm going to basically create a pool of 10 actors, and I'm going to use a broadcast router in Akka.NET to push 100,000 messages through the system. So that means that we're actually doing about a million messages in here. That's going to allocate 104 megs of memory. And then I'm also going to do a test with 10 million megabytes, 10 million messages as well, which generates about a gig of total memory pressure. And you can see here that we have roughly the same number of Gen 1 garbage collection attempts here. This is all probably the concurrent queue allocating new segments as our mailbox size grows. But the number of Gen 1 allocations is Gen 0 garbage collections is way higher, roughly 10 times higher in our other benchmark. So all of this seems pretty consistent so far. Now, what happens if this data was all collected with our envelope as a class? What happens if I convert an envelope back into a struct again? Well, lo and behold, I'm seeing my 33% memory savings that we saw earlier happen again as well. We go from using 104 megs to 71, go from using 1 gig to using two-thirds of one. And the issue in this case is that that cross-thread access actually makes a difference in terms of our total amount of memory pressure. And the reason why is that even though when we're running on a single thread, it's more efficient to use a class once since it's passed by reference and it's all instantly, Gen 0 sort of garbage collected by the time we're done. Well, when I'm passing around objects between multiple threads, like how I am in this system, that copying all happens only when that thread is scheduled. So those, let's say that those copying operations become a lot cheaper than the garbage collection operations would otherwise need to have inside the system. So you'll notice, for instance, that we went from having 26,000 Gen 0 garbage collection attempts to only 18,000. So, in addition to removing, let's say, one third of our total memory allocation, we also removed one third of all of our Gen 0 garbage collection as well. So, that's one of the reasons why ultimately changing this back into a value type makes more sense in the grand scheme of things. The other thing you'll notice, by the way, is that the actual performance numbers down here were negligible. The performance improvement between, let's say, the performance difference between using a value type and a reference type was practically not measurable in the system. And that's probably because we had some other sources of overhead that were more significant than that inside the system. Which brings us to our final section of today's presentation: threads, memory, synchronization, and pain. Now, the whole reason why most developers start looking at Akka.NET in the first place is because concurrent programming is hard and unpleasant. And this is why it is hard and unpleasant. The first thing we should talk a little bit about is thread local memory, or thread local storage is probably the common term for that. Thread local storage is a concept where threads get memory that is always associated with them each time they execute. It's dedicated sort of thread local memory that is where we allocate things like thread static and thread local objects in C sharp. Objects stay there and are available each time the thread is scheduled to run. So thread static objects are ideal for doing things like caching and pooling. So a good example, inside Akka.remote, we have an LRU cache, least recently used, what that stands for deserializing actor references, because that can actually be a somewhat expensive operation. We use thread local caching for this because that eliminates the need for us to have to synchronize between threads, meaning we don't have to use any locks or semaphores or anything like that. And on top of that, we also have really good cache affinity. All of the data that we need to do our work is being done in a very adjacent sector of memory to the thread that's doing it, meaning the thread local memory is basically probably going to be, if that thread's running frequently, probably going to end up getting cached inside the CPU that we're on if we have CPU thread affinity, which is not necessarily a guaranteed thing. And that means that our access times are going to improve and we're going to be able to get lower latencies when we do that. The downside of thread local data structures is also their strength, which is that they aren't synchronized. This means we can have multiple variants. So a good example, if I'm on thread 1 and thread 1 just deserialized a message from actor A, and then thread 2 is the next thread that gets scheduled to process messages from that socket again. And we also have another message from actor A on there. I can't use the cached value that we just wrote into thread 1's thread local data structure. I have to go ahead and have a cache miss all over again and reproduce that work. That's an example of variance, meaning that the data looks different on a per thread basis. Now, in a super busy system, it doesn't make any difference because all of that will average out after, let's say, a minute of heavy usage or so. But in a system where you have lots of intermittent work occurring, that might be more noticeable, and it might be better to use a synchronized cache in those environments. This is why we do tons of benchmarking in Akka.NET. Now, the real cost of threads, and in terms of, let's say, memory access, is typically their memory switch, their context switching overhead. Um, Context switching is something that happens in every operating system, in every runtime, in every programming language. It's not specific to .NET. But the idea is that basically, reference types pass between threads, typically age into older generations of garbage collection. So if I have an object that was previously used on this thread and is now used on this thread, that object's going to get rooted in multiple places. If it's rooted by a thread that's not currently executing, then we can't garbage collect it right now, and therefore it's probably going to age into those older and more expensive forms of garbage collection. That's one way in which context switching drives up some costs. What context switching actually is, in fact, I'll just show it on the next slide here. Context switching is when one of two things happens. First is, let's say we have CPU 0, CPU 1, and we have thread 0 and thread 1 are both executing on their respective CPUs. Each one of these threads will be given 30 milliseconds by the .NET runtime to execute before that thread has to yield execution to another thread behind it. Well, when thread 0 is done with its 30 millisecond quantum and it's no longer scheduled for work, that way another thread gets a chance to run. We want to make sure that all threads get an opportunity to run so we don't accidentally starve a thread that has work to do from being able to perform its job. Thread 0 is going to get rescheduled. It has more work to do. Well, if thread 0 gets scheduled onto a new CPU, a different one than it was on before, that's a context switch. Any of the cached objects that were used on the L1 or L2 cache built into the CPU can no longer be used to service thread 0 because now thread 0 is going to be executing on a different CPU than it was on before. That's one way context switching can occur. The other way in which context switching can occur in .NET would be if, let's say, we had an async await, let's say, piece of code, and we awaited on this thread, and then when our await was complete, the continuation function, the continuation task executed on this CPU. That would be another example of context switching where that work got moved from one core to another. In this case, the work might be getting moved between threads as a result of just the who was available to service this item in the .NET thread pool at the time, right? Whenever that occurs, we have to transfer memory from the actual, let's say, shared memory bus back down to the CPU. We can't take advantage of local caching when this works. And that's going to result in higher latencies, takes more time to transfer memory from the memory bus down to the CPU. And on top of that, there's going to be a certain amount of rehydration that has to happen when actually, like, let's say this piece of code gets executed back to the CPU again it's because we have to retrieve that data from the memory bus. So context switching can have a really high latency impact on our applications. This is an example of something we've been working on for Akadon 1.5 that demonstrates what that impact actually is. So one of the new things that we did in Akadon 1.5 is we've taken advantage of this iThreadPool work item interface. This was added in .NET Core 3.0, and this allows us to avoid allocating a delegate every time an actor executes on the default .NET thread pool, which is nice. However, there's an additional property that's very useful when we work directly with the .NET thread pool, which is when we call thread pool unsafe queue user work item, which is how we're passing in one of these thread pool work items here. We have the ability to specify that we prefer local execution. This means that we're telling the thread pool, I would like you to attempt to reschedule this work item on the core that we're currently running on right now. This is essentially a kind of abstract way of being able to tell the runtime that I want to have a degree of CPU affinity for this thread. So this work item should try to execute on the same thread on the same CPU that's currently running right now. Now we have a benchmark that's really good at being able to measure the impact of this. This is our in-memory ping pong benchmark. And these values on the left refer to the dispatcher throughput of Akka.NET. Akka.NET out of the box has a way of being able to batch multiple operations together onto the same quantum of time in the .NET thread pool. So it automatically has a built-in way of reducing context switching out of the box. And that's by having a dispatcher throughput value of about 30 by default. However, if we set the dispatcher throughput value to 1, then we basically behave the same way the .NET thread pool does, which is that Every single task we execute has a unit of work size of 1 rather than a unit of work size of 30. And so the opportunity for context switching is much higher with this value than it is with this one. So this is using, let's say, Akka.NET 1.5 before we added that change to the .NET thread pool. This is Akka.NET 1.5 after adding that change. And you'll see that we have a 3x improvement in throughput here as a result of eliminating context switching. This is because we're able to take advantage of caching at the CPU level. We're also able to essentially keep the same thread executing with the same work over and over again when this occurs. So the scheduling delays are a lot smaller inside the system. So we went from about 9 million messages a second to 27 million messages a second. Let's take a look at the other extreme end of the pole down here, where we have a throughput of 900. We still see a 50% improvement in performance over what we had before this change went into effect. So even though this was, in theory, the setting that should have been affected least this is the setting that should have been affected least by those throughput changes, it still demonstrated some impact as well. Now, there's definitely going to be diminishing returns. Once you get above a throughput value of 30, which is the default on Akka.NET, the numbers start to become a little bit more random because at certain points, the operating system scheduler is going to put that thread to sleep, even though it has more items to work on. So we can't necessarily, how do I put this? We basically can't guarantee that we're going to get a chance to process all 900 messages before either the .NET runtime or the Windows or Linux operating system forces this thread to yield for somebody else. So that's the advantage of being able to specify where we want execution to occur, and it allows us to reduce context switching. Some of the parts of .NET 6 that are built into the runtime, like the task scheduler, already take advantage of this for you. So you should see your awaits complete a lot faster if you have a lot of them than they did before, because they're taking advantage of this exact same change as well. So when there's no context switching, here's what's really occurring. Thread 0, instead of being scheduled on a CPU 1, thread 0 gets executed back on the same CPU it was previously executing on. That way we can try to benefit from locality of memory access and from the availability of caching inside of here. Now, the next and the last thing we're going to focus in on is synchronization. This is the big dreaded area of shared memory concurrent programming that we try to avoid entirely by using Akka.NET actors. This is the message queue data structure that the Akka.NET mailbox uses internally. It's just a concurrent queue. And one of the things I noticed is that the concurrent queue, I noticed the Gen 1 garbage collection on one of the other benchmarks that we ran. And I said, I guarantee that Gen 1 garbage collection is coming from the allocation of new array segments inside this queue in order to support, let's say, increasing amounts of demand for data storage. I wonder if we could, in theory, improve upon that by switching to using a linked list. That way, I can potentially avoid having to allocate new memory segments each time our concurrent queue grows beyond some certain threshold. So I took a look at what the existing sort of performance looked like, their concurrent queue data structure, and I came to the conclusion that we're allocating basically 385K when we're attempting to put messages in the queue, and about 3.1 megs when we're doing 100,000 instead of 10,000. Okay, let's see if we can improve upon this by using a linked list. So I'm using the generic linked list data type that's built into systems.collections. But you'll notice I have to create a lock. And that's because this data structure is not thread safe by default. The only data structures that are thread safe in .NET are going to be the systems.collections.concurrent, which will be things like concurrent dictionary, concurrent queue, concurrent bag, or it's going to be the systems.collections.immutable. Those are also technically thread safe, but the way they achieve thread safety is very different. They don't use synchronization. They basically use immutable programming models to do that, and it requires a little bit of math to basically make those work properly when you're, let's say, assigning them to a field. But that's neither here nor there. Let's go ahead and just focus on this data structure for now. So we have our linked list, and for every single both read and write operation on this linked list, we have to go ahead and lock it like how we do down here. We have to use, this is called a monitor in C sharp. We have to use this monitor to make sure that the access to this data structure is synchronized across all the threads that might need to read and write from it. So let's see what the performance looks like with this data structure. We go from allocating about 310 kilobits to 547, and those numbers keep going up the more we drive up our memory performance. And then on top of that, we go from a in queue performance of about, I think on the previous slide it was under 200 microseconds to over 500 microseconds. So it's more than 2.5 times slower than what we were doing before. So this was a big fail. Why did that happen? Well, the answer is that concurrent queue is, for all of its drawbacks, is actually exceptionally performant. One of the reasons why it's so performant is it avoids the use of locks. Lock contention is a measurable, let's say, source of throughput impact inside your applications. And basically, locks should be used when you don't really have another option. If you have a really complex critical region of code where there's shared memory in there and there's no other way to synchronize it, you probably end up having to use a lock. Um, the concurrent queue system does not need to do that. Instead, it uses volatile memory, which means that it has memory barriers that force all the other processes to refresh the value of the registers of this object each time they access it. And then it uses what's called a compare and swap operation, like interlocked.exchange, for instance. It's interlock.compare exchange to actually swap out segments of memory when they're added. This can be quite a bit faster because they can be executed in many fewer CPU instructions, and they ultimately reduce lock contention overhead. The downside of using these methods here is that they're much more complicated to get right. However, Microsoft is the sort of company that can afford to do this really well at fairly low cost. So, as a software developer, you don't necessarily need to worry about that. If there was something seriously wrong with the concurrent queue data structure, Microsoft would find that pretty early on. Now, even on a single thread, these compare and swap operations are going to be significantly cheaper than using a lock. Here is the other downside that we found here, which is that the linked list, our assumption about it being more memory efficient, turned out to have been was deeply flawed. And the reason why is that concurrent queues only allocate data structures when the requested queue size is bigger than the current queue size. And it'll essentially double the size of its internal array each time it does that. And then it will copy the values over. That's how it used to work. Today, I think it's even more efficient than that. I think it just allocates a new array segment and adds a new reference to it. But so that way we're only allocating the new memory that we need, not shuffling around the old memory that we can kind of keep. Linked list data structures, on the other hand, allocate a new object every time we perform an insertion. And that ends up being much more expensive than just using an array construct to do that. The other downside of a linked list is honestly the built-in version of it in .NET absolutely sucks. You would probably be better off rolling your own version of a linked list that use, let's say, if I really wanted to go nuts, I could try to make envelope into a class structure and have that function as a linked list. And that would probably be a much more efficient way of implementing this. There would be a lot of downsides to doing that, namely that it would be impossible to broadcast a message to multiple recipients if we did it that way. So that's one of the reasons why we won't do that. But that's one of the things you should think about when considering, let's say, trying to beat the performance of something like a concurrent queue. Is that it's not as easy as it looks. So that's it as far as my show and tell presentation is concerned. I will post a copy of these slides online. In fact, I think they're already available in the meeting minutes for today's presentation. But thank you very much for your time today. And if you have any questions about anything that I covered in this presentation, I'll stick around to answer those for a couple of minutes. Gregorius, do you have any questions about anything that we covered?
No, we pretty much discuss all of this in Discord. So
Yeah, we do. Inside the Akadana Discord, we do this type of performance work all the time. The one thing I'm definitely a big growing fan of is using the writer dynamic program analysis tool. I find all sorts of stuff every time I do that. I'm looking forward to giving that a try actually on I'm probably going to do that inside some areas of Akka Streams and inside Akka Persistence as well. I think there's probably a
Mhm.
lot of low hanging fruit to be had there that we can performance improve upon. All right. Well, with
Uh,
that being, oh, go ahead, Gregorius.
One thing though, you mentioned the GC system between the workstation and server.
Yes.
I would say I would think that the server model wouldn't really work in the cloud environment.
Well, it actually works pretty. So the one area where server mode GC might have some trouble would be an environment like Kubernetes. Actually, server mode GC works great on environments like Azure, like app services, or when you're running on bare metal virtual machines. And the reason why is that you have control over the tenancy factor to a degree there, and you don't have to worry about side effects from other processes, GC threads interfering with other processes. But in a
Mhm.
densely packed environment like Kubernetes, if everyone's running on server mode GC, a lot more of the total CPU for each one of your nodes will be eaten up by garbage collection from all the processes that are densely packed on there. So there is some overhead to doing that. That being said, the end-to-end sort of throughput of your system will still probably be higher, but you're going to run into a lot more memory consumption and a lot more memory consumption and a lot more total CPU utilization if you do that. My guess is if you talk to someone who's running a really large scale Kubernetes system with .NET 6 on it, my guess is they're running server mode GC and it's probably fine. That would be my guess. That advice they
That's
used to
true.
give about multi-tenancy and workstation GC was really for when people were trying to run like web 1.0 hosting businesses with like thousands of customer sites all running on IIS, right?
Mhm.
Um, that's what that advice is really for. In the era of multi-core cloud computing, where things are a lot more efficient and the garbage collector works a lot better, my guess is you'll probably be okay. Even running that on a densely packed Kubernetes machine, I don't think you'd have huge negative performance ramifications for doing it. Let's see. Any other questions in chat? Nope, I don't see any. Well, thank you everybody for attending. Hope you enjoy the talk. I'll make sure I tweet out a link to the slides a little bit later today. But also, please don't forget to like and subscribe. We really appreciate it. And thank you again for attending our community stand up. We always really appreciate doing these. And next month, we'll have a speaker from one of our companies who's using Akka.net to automate a whole bunch of agricultural work. They'll be coming on and presenting about their use with Akka Cluster and Azure Container Apps and all sorts of fun stuff. So until then, we will catch you in November. And thank you very much. We really appreciate everybody in the Akka.net community. Take care.